Hi, my name is Adam. This is my Design of Logic Systems final lab. I did the rock, paper, scissors project. I'm in lab section 33. And for the rock, paper, scissors lab, I basically just had to make a board that let someone play rock, paper, scissors against someone else. Switches 0 to 32 were dedicated to player 1, 13 to 15 were dedicated to player 2, and if player 1 wins, it had to display a 1. If player 2 wins, it had to display a 2. And if neither one, it had to display a T. And if any other case, so like anything went wrong, say one of the players did 2 switches, it had to display an E. I did run into a bit of a problem with trying to do a T because we were using a 7-segment display on the FPGA board, where T's aren't really possible in that. So instead of a T, I ended up using an equal sign. Um, I initially thought of using a D instead of the equal sign, but I kind of decided to use the equal sign because it made some of my truth table easier and it made my K-maps easier. This is my truth table. Here you can see the conditions where each thing happens, like a tie, player 1 wins, player 2 wins, nothing shows up, uh, or the E shows up. You can also see that what each thing is, what each thing is. So like switch 0 being rock for player 1 and switch 15 being rock for player 2, things like that. You can also see that I had 7 outputs because there are 7 different LEDs for the 7-segment display. Here are the K-maps for each of the outputs. Uh, for the there are 7 outputs, but there are only 5 K-maps because a couple of times 2 of the K-maps would be equal. Like in this case, A was equal to E, so instead of having a different K-map for A and E, which would be the exact same, I just ended up having them be there together. Something else that's interesting to notice is how massive these equations are. That is because the equations are so massive because the first off the k maps themselves are massive. They're 6 variable, which means they're 8 by 8. They're just really big, and you see how each of the circled things is not next to any other thing that's circled. That means I wasn't able to minimize the equations, which means the equations ended up being fairly large. Here's the code which I used. It was just very similar to the code I used in pre-lab 12. I basically just used a lot of the same ideas. I used that as a template more or less. And this is the biggest difference was the case statements. So the case statement for this one had a lot more cases. It actually ended up having 64 different combinations. And to kind of make sure I didn't have to write 64 different combinations out, I used a default case here for anything that would have an E show up, because by far there were more E's than anything else. There ended up being over 50 E's versus for over 50 cases where an E would show up versus the 10 or so where literally anything else happens. Here's the first video of my implementation. This video shows what happens like for each of the twos winning, ones winning, ties, things like that. So to do this, I started with one of the twos flipped, and then I just flipped each of the ones on, off, and then on, off. And then I flipped down that 2, and then flipped the next 2 up, and just repeat it again. This shows that each and every one of the cases where a player would win or the players would tie does work. And then in this video, I do more of the messing around with the showing when E comes up. And again, E comes up in a lot more situations than anything else. So I doubt I did every single combination where E would show up, but I do believe I showed enough to settle any doubt that it works very, very well. Thank you so much for watching, and have a nice one.